Okay. Good morning, ladies and gentlemen. Welcome to the 2021 International Symposium of Precision Environmental Medicine, Emerging Scientific Links Between Air Quality and Health. On behalf of the conference, I'm delighted to welcome you all this online conference. 欢迎各位贵宾莅临2021精准环境医学国际研讨会，空气品质与健康之新兴科技连结。我是施以威德，仅代表大会很高兴欢迎大家参与这次线上会议。In the very beginning, I would like to introduce our distinguished guest online today. And now it's given me great pleasure to present you Professor Tim Bauzong, the chairman of our conference, and the director of the National Institute of Environmental Health Science and the National Health Research Institute. Now we are very delighted to the chairman, Dr. Chen, to make a statement. 首先，让我们来欢迎介绍今天与会的贵宾演讲者。现在很高兴地向各位介绍我们今天的大会主席陈保忠教授，目前也是国卫院环医所所长与公卫学会理事长。请主席陈保忠所长致辞。
各位线上的与会贵宾，大家早安，大家好。我们就开始今天的2021年精准环境医学研讨会的开会了哈。那我今年的主题当然最主要是围绕空气品质与健康强调它的新兴科学的连结啦。那这次呢，我们这个研讨会呢，也结合了台湾公共卫生协会整个联合年会的活动。那这个是今年公共卫生联合年会从今天开始起跑，一直到这个礼拜天10月3号。那今年年会的主题是大疫情时代下全球公共卫生的冲击与挑战。那我们这个研讨会的议题空气品质与健康，我想更符合在全球卫生的这个议题。那大家也知道这个空气品质的议题不只是国内的民众关注，那在全球的所有的国家、所有的民众都非常关注的议题。那特别，我想贵宾们大概都知道，我们在去年在上个礼拜9月22号，WHO 也宣布了这个全球的air quality 的 guideline 那在这个 guideline 之下呢，我们还有很大的空间，可以在努力的地方。所以，今天的研讨会呢，我想，我们就邀请到国内外的一些重量级的学者来共同参与，特别是日本的 Shachiko Hojo 教授哈，还有我们远在美国的Longji陈教授哈，还有事实上我们的团队里面的郭卫良教授也在澳大利亚哈，所以我们希望今天的活动呢，针对这个环境的议题，特别在空气污染上面的怎么样去精进哈，我想不止这个所谓的精准，不只是在环境测量的精准，我们更重要知道治病的机转因果关系甚至是个人的易感性才能有一个精准的政策的介入，精准的个人的措施。所以这些议题的讨论呢，我相信对日后我们的空气品质的改善会有重大的贡献。那最后呢，再一次谢谢所有的演讲者，所有的线上的与会的贵宾在今天的共同的参与。在这全球 COVID-19 疫情之下呢，我想我们更需要 有清新的空气可以呼吸。希望我们共同来努力，最后敬祝大会圆满成功。谢谢各位，谢谢。
Thank you, Director Chen. Today, we are very delighted to invite Liang Genyi, the President of the National Health Research Institute, and Yang Junyu, the President of Kaohsiung Medical University, to give us the opening remarks. Welcome to the President Liang and the President Yang. 今天我们很荣幸能够邀请到国家卫生研究院的梁根义院长与高雄医学大学的大家长杨俊义校长来为我们致辞。现在就让我们用热烈的欢迎，来欢迎国家卫生研究院梁院长的致辞。
梁校长、陈所长以及线上与会的贵宾，大家早安！欢迎各位出席2021年精准环境医学国际研讨会。国家卫生研究院的国家环境医学研究所以实证医学研究为基础，着重预防或减少环境有害物质对国人健康危害及影响，并透过新颖技术提升医学研究品质，希望以环境科学教育概念转译作为政府单位之研究智库。目前针对现今国内外最重要的议题，也就是空气污染进行防治策略的研究。根据 WHO 全球疾病负担报告，他们推估2017年因为室内室外环境空气污染所造成的死亡人数达到470万人，共造成1亿4700万损失的人年。那死亡呢，以缺血性心脏病、慢性阻塞性肺病疾病、下呼吸道感染为主，其中呢又以亚太地区最为严重。然而，空气污染防治策略需要整合多项跨领域的资讯，包括暴露评估、毒理、流行病学、数据分析、健康风险评估与政策转移等领域的合作，才能够厘清及有效防治空气污染对国人健康的影响，也是现今国内外最困难的环境医学议题。2021年精准环境医学国际研讨会以空气品质与健康之新兴科学连结为研讨的主题。我们邀请了国内外具有声望之学术及跨学科研究学者，提供精辟的研究，包括环境、流行病学、暴露科学、毒理学、系统生物学研究、数据和分析科学、空气品质物联网应用与室内空气致敏性等议题等相关问题与技术，希望能借由此次与国内外不同领域专家学者交流讨论，完整的汇整出合宜可接受的精准环境暴露与健康风险的研究方式或改善措施，来提出控制地区的空气污染与合宜政策，期待朝向空气品质之精准环境医学目标迈进。那最终希望是同时可以推动环境医学的教育、研究与服务，以提出本土环境暴露的健康影响的相关政策，提升国民健康，彼此举行空气品质与健康之国际会议更具有意义。最后预祝精准环境医学国际研讨会顺利成功。提升国民健康，彼此举行空气品质与健康之国际会议更。
Thank you, President Liang, to speak. And we also invited President Yang to give us our opening remarks. Welcome. 现在我们也用热烈欢迎高雄医学大学杨校总来替我们致辞。
国家卫生研究院梁根义院长，国卫院国家环境医学研究所陈保忠所长，各位与会先进，各位女士、各位先生，大家早安。今天非常荣幸代表高雄医学大学欢迎大家。很可惜，这次因疫情改成线上会议，无法以东道主的身份来招待大家。但是也感谢各位专家学者们愿意以线上莅临指导， 期待跟各位一同关心空气品质与健康之新鲜科学连结之精准环境医学议题。近年来，空气品质与健康防护已经是全球迫切关注的公共卫生与环境医学议题，不仅需解决因空污对各类疾病所造成之负担与影响外，对于国家整体经济之关联性亦不容忽视。而在目前的研究中，流行病学关系之建立、空气品质暴露评估，包含成分组成与来源的鉴定，以及人体间异质性与易感受性都存在相当的不确定性。鉴于此，追求空气品质与风险识别、健康风险评估、风险控制的精确性，一直是这个领域想要努力实现的目标。同时，也希望相关的见解及回馈能提供给政府单位，作为未来公共卫生及环境医学相关领域之政策规划上之具体科学实证与依据。2021年精准环境医学国际研讨会将聚焦于空气品质与健康之新兴科学连结，并邀请国内外具有声望之学术及跨学科研究学者提供精辟的研究分享，包括环境流行病学、暴露科学、毒理学、系统生物学研究、数据和分析科学、空品质联网应用与室内空气致敏性议题等相关问题与技术，内容丰富精彩可期，期待能朝向空气品质之精准环境医学目标迈进，长此以往，吸引更多人才投入这个领域，为国民健康和福祉努力。再次的感谢梁院长、陈所长促成这么好的会议，让有志一同的人得以尽情的交流、交换新知、相互切磋。俗话说，好的开始就是成功的一半，相信这一次会议一定是非常的成功。谢谢大家，也祝大家身体健康，万事如意。
The next agenda is a group photo. And try to open your camera on the web assistant to take a photo. And now we, Professor Hojia and Professor Zhuang, yeah, okay. So 接下来的议程是线上大合照，请线上的师长贵宾们帮忙打开 Webex 上面的镜头，让我们合照留影一下。Okay. So 何老师也在线上，林老师、郭老师，好，然后我们数1、2、3，然后我们就是拍一个大合照这样 ，OK，1、2、3。Smile。子伟，你那边会帮忙拍吗 ？OK。One more。1、2、3。So。And thank you for all professor and discussion guests. 谢谢所有的教授和我们的现场的来宾。Okay, ladies and gentlemen, let us announce some important things. Because this conference is online conference, so we in the online discussion session we open the chat room on YouTube to the audience. So please feel free to ask any question or share any thought with our speaker. We hope everyone who enjoying this wonderful presentation. 所以在大会这部分有一个重要的事情先跟大家宣布。我们在 YouTube 上面会向观众开放一个聊天室。如果任何有意见，对任何建议或任何想法，请在那个 YouTube 上面的聊天室可以提出，我们会请工作人员交由主持人统一提问。Okay, so let's take a short break right now. The next session will start in 20 minutes. Thank you. 所以我们接下来要请各位贵宾跟各位的听众稍微休息一下。我们下一个议程将于20分钟后开始，就9点50分的时候开始。谢谢大家。Thank you all for your patience. And now for the first keynote speech, speaker is Professor Chen Longji. We are honored to have Professor Wu Mingchang of Kaohsiung Medical University and Professor Lin Pingping of National Health Research Institute serve as our moderator. Now, let's welcome Professor Wu and Professor Lin. 本大会第一次场次演讲，讲者为陈龙纪教授。我们很荣幸邀请到高雄医学大学公共卫生学系以及环境医学研究中心主任吴明昌医师和国家卫生研究院环境医学研究所林平平研究员担任主持人。现在让我们欢迎吴医师和林研究员。
Good morning, everyone. Welcome to the first section of 2021 International Symposium of Precision Environmental Medicine. Dr. Lin and I, we co-chair this this first session. And I'm Mingchang Wu from Kaohsiung Medical University, and Dr. Pingping Lin from the NHRI. First, I'm going to introduce our keynote speaker, Dr. Longji Chen. Dr. Chen graduated from National Taiwan University in 1976. Later, he went to the USA to pursue his graduate degree, and later he received a master and a PhD degree from the New York University, major in environmental medicine. And after his graduate, he went to the MIT to become the research scientist. In 1994, he came back to the NYU School of Medicine to become the assistant professor at the Department of Environmental Medicine. And right now, he is a full professor in the same department. And Dr. Chen is an international recognized expert on inhalation toxicology. And he has extensive experience to study cardiopulmonary effect related to inhaled pollutant. He also served quite a number of international committee and the study section in his expertise. And right now, Dr. Chen is already publishing more than 200 research paper and book chapter. So he is quite experienced on the air pollution, inhalation toxicology, and also the adverse effect of cardiopulmonary disease. So right now, he is going to talk about the toxicology study of health effect of a particular metal component. Let's welcome Dr. Chen.
Yes, thank you very much for the introduction. And I'm honored to be invited to this meeting. And especially,我是公卫第一届毕业生，所以感觉更荣幸能够跟公共卫生学院一起有同样的会议。Okay, today we're going to talk about the toxicology study of the particulate matter components, and this is based on several years ago we completed a more comprehensive study, and I'm going to present some of the data of animal research, chronic exposure to concentrated ambient particle, as well as in vivo and in vitro short-term exposures. And toward the end, I'm going to introduce some more recent health concern about wood fire in California. And it's kind of a special event that PM component actually is a very important factor in terms of their risk assessment. So okay, this is my collaborator, both in NYU and at another university. And you can see later that this research involved 4 different other institutes other than NYU. And these are my collaborator in those institutions. And today we're focusing on particle. This is a particulate matter present in the ambient air pollution, and have the variety of different sizes. And most important component of these particular fraction is the smaller than 10 micrometer, as well as smaller than 2.5 micrometer. We call it PM10 and PM2.5. The research on particle pollution started in 1952. I think a lot of you are probably familiar with this episode. And during that 1 week period, there's a tremendous amount of air pollution that you can see that even during the daytime, you need a person to the bus to guide the bus around the city. Otherwise, the driver cannot see anybody. So the concentration of PM at that time is enormous. And so you can see that changes in concentration is corresponding to rises in mortality. Number of people die during that period. It's about 4,000 to 6,000, and it did not go down to the baseline level even 1 week later, and it lingered around for several more months. My colleague Cassie Ito and George Thurston, during that time, the only parameter they monitored in the London episode is SO2 and SO2 and British smoke. And you can see that British smoke is equivalent to about 4.46 milligram per cubic meter. We never see this type of concentration that much in the modern days. And Cassie Ito and George Thurston reconstruct that based on these 2 parameters. They estimate the possible concentration of sulfuric acid during that episode. And they do the correlation. You can see that the sulfuric acid actually correlated better than the British smoke or sulfur dioxide by itself. So this is the first indication that perhaps the component other than what you are measuring is actually contributing to the health effect of London smoke. And modern days, right now, the concentration is much, much lower because all the government implement the PM reduction technology. And however, if you compare the 2 studies, one conducted in between 1982, using the population of 1982 to 1998, the ACS cohort versus the AARP cohort, that is between 2000 and 2009, there is about 30% reduction in there's a 30% reduction in PM concentration, but there is no corresponding reduction in mortality, which means that what we can do to reduce all the government measure to reduce the air pollution is removing those components that are not really that much very toxic. So all the toxicity remain even though with a 30% reduction in PM. So we need to find out, even at this low concentration, what is the component that are responsible for the adverse effect that we are seeing in the PM pollution episode. PM are entering the body mainly through the lung, but they can also enter through the blood. They penetrate it from the lung epithelium into the bloodstream, or go through the nasal cavity and olfactory bulb to get into the central nervous system. And then once they get into the body, the systemic oxidative stress inflammation is responsible for most of the cellular response in each of the organ system, and that produce adverse effect, eventually leading to mortality. And you can see that there's a variety of organ system is affected. And as a matter of fact, that whichever organ that we look at, we will always see some changes in mortality, changes in the organ system. And this is a molecular pathway that are responsible for the cellular change and organ system change in the body. To me, this is it's not as important as if we can stop the pollution to enter in the body to prevent this from happening. And once the particle get into the body, not much you can do to reduce the toxicity. So what my interest is to find out what is the pollution before you enter in the body, what kind of it, what is the source category that can respond for the change. And once we know that, we can use the pollution policy to reduce the exposure and at the same time reduce the impact of PM exposure. Okay, so this is a typical pollution from the automobile emission, from power plant, from factory, from secondary aerosol, secondary formation. It can produce toxic component. And so if we can figure out which one is responsible, and we can have more effective control measures. And back in early 2010 or so, NYU has a very comprehensive study to look at the association between the PM chemical component that are responsible for the changes in human and in laboratory animals. And that study is called National Particle Component Toxicity Studies, briefly called NPAC study. This is funded by Health Research Institute, and in that study we have four components, and each one George Thurston and Casito is responsible for human study. They're looking at the chronic exposure and acute hospital admissions. And Terry Gordon and I are responsible for for the animal study and in vitro studies. And in the US, because this is a big country, the source of PM have very unique distributions. And in terms of traffic, it's over the place because it's a car-oriented society. So you can see that traffic is over the place. But for oil combustion, you can only limit it. The largest contribution of contribution of oil combustion PM is mostly located in the northeast of New US, along with some of the large seaports. And for the biomass burning, it's almost evenly distributed. But during the winter, most of the northwest are using the biomass burning as a fuel source. And for coal combustion, and most of the power plants are located in the Midwest because the location of the fuel source. So the west-east of the northeast region of the U.S. are dominated by coal combustion emissions. So we choose 5 locations to do our study, and we simultaneously did an exposure in Manhattan and in Tuxedo, New York. It represents the urban and rural exposure. And we go to East Lansing to look at near the Ohio Valley, to look at the coal combustion, and also industrial, because there's a lot of steel mill around the area. And in the winter, we went to Seattle, Washington to look at the contribution from wood smoke, and in Irvine, California, and we're looking at the contribution from traffic. And we did the concentrated ambient particle concentrated system called CAP system. We concentrate the ambient particle 10 times, and we do exposure for 6 hours a day, 5 days a week for 6 months, and 5 different locations. And we did continuous heart rate and heart rate variability monitoring using telemetry. And we also are using ultrasound measurement every 2 months, and eventually sacrifice the animal doing the histology to look at the long-term effect on atherosclerosis. And this is the system we use, and it's fairly compact. And I'm not going to get into the detail of this system, but it's a small system, about 3 feet by 5 feet around, and we can move around the system to different locations, different universities. And so we eliminate some of the variable associated with the exposures, because the same system is used for most of the exposure, for all the exposure and different locations. And this is we did a pretty good job of concentrating the ambient particle between 6 to 10 times, and by different locations. The ambient level varies, so is the CAP concentration, and both the black carbon and organic carbon also vary between these locations. So we take advantage of the changes, the difference between different locations, so we can figure out what is the component using source apportionment analysis to figure out what is the component they are responsible for the change that we see at each of these locations. And we did the continuous monitoring for heart rate and heart rate variability. And you can see that it varies between time of day, between different locations, urban and rural, different time of day, even different day of exposure. So this change actually is tracking very well with the PM composition change. We took a daily sample at each location each day, and we used the XRF to look at the concentration of each element, 37 elements. and we do the source apportionment analysis and figure out what is the source contributed to the change in the heart rate and heart rate variability. And the number of significant change from this cardiac function and is related to the adverse effect. And we're looking at how many number of change on these parameters and sum it up. The larger the number you see, the greater the health effect on the cardiovascular system there is. So right away you can see that New York City has many more different sources, and then the Sterling Forest, the rural area, and they have greatest change to the cardiovascular system. Residual oil is one of the major fuel source to heating of New York City area and has greatest change. And traffic is also part of the a source that contributed to that. Some of the industry is still around at that time, and sulfur coal combustion also related to the change. We can also pick up fireworks. The July 4th, Macy usually have a firework, and we can actually pick up the health effect associated with firework. Firework contain a lot of metals, and we actually can see the contribution from that. And Sterling Forest, the New York rural area naturally has a less PM concentration, similar concentration, but they don't have a lot of primary emissions. They have a lot of secondary emissions, secondary aerosols, and we can pick up coal combustion and nickel refinery from this source. And Seattle and the Irvine LA area is mostly related to the traffic, and the soil can't come up to be the first component to be seen, but soil is not really directly, it's really a resuspension of the soil by traffic. So the soil component actually is a part of the traffic dust related to that. And in Seattle during the winter, we actually pick up wood as one of the contributing factor. In East Lansing, coal is one of the important factor, and some of the industry also contributed to that. And you can see the soil is from all the site that we see. This is because New York, U.S. is a car-dominated society, and resuspension of soil from traffic is become one of the major source of for the PM that contribute to the adverse effect. And we use the ultrasound and in-fast atherosclerosis area, as well as the cross-section of the aorta to look at the chronic atherosclerosis resulted from PM exposure. And very interesting is that we only see changes in the East Coast, okay, in area of New York City and also East Lansing, because the area are impacted more by conditions. In the West Coast, we did not see any change in atherosclerosis because the coal combustion, they don't use the coal combustion as their power source. So the pollution is not there, and the chronic effect that we see with the PM exposure are related to mainly related to the changes in from the coal combustion pollutions. So this is just some short conclusion. The heart rate variability are associated with changes in the PM exposure. The rate of change is vary with different site and different time point. It's mainly related to several important source category. For the long-term plaque progressions, coal combustion is one of the major reasons for the RVS effect. And for our in vitro study, and also called oral pharyngeal aspiration study, we collected particles from locations that we conducted chronic animal exposure. And we use a system called CanVolt to collect the coarse, fine, and ultrafine particle, and we extract that and expose to the lung epithelial cell or pulmonary endothelial cell, as well as the cardiomyocyte. And we use the viability and reactive oxygen species production, fluorescent from the dichlorofluorescent compound, and we also look at the cytokine productions. For the oral pharyngeal aspirations, we look at the lung lavage endpoint and how many neutrophil is present, and also cytokine concentrations. And so we look at the contribution from 5 different locations, the site, and we look at 3 different sizes, and we look at 2 different seasons, winter and summer. And you can see that everything is important. So location make a difference because different locations have different compounds, and size is different because size is related to how the aerosol is generated. Season also affecting the aerosol's fate in the atmosphere, as well as the source, or what source is being produced. And there is an interaction between the site and size and season, but there's no interaction between site and season. So everything is important. So if you want to look at that, what is the component they are related to the in vitro cellular response, we have to separate into location, different size, and different seasons. And we also look at the soluble versus insoluble. A lot of people have a belief that soluble part of the PM is probably more toxic because they can get into the body easier. But on the contrary, we see that in most of the cases, the total PM, and this is the size, including the insoluble part of the PM, actually produce much greater response than soluble part, because once the particle is engulfing the cell, they can stay there a lot longer and produce greater effect. Soluble fraction, once you get into the cell, will be dissipated and disappear and be metabolized or whatever, and so it disappear quicker and produce much less effect. So we had to look at the total PM instead of just the soluble fraction. And this is the correlation between the change in ROS at the 2 different cells according to the different element of the PM. The usual suspect that can produce participate in Fenton reaction are here: copper, iron, vanadium, nickel. These are elements that can participate in Fenton reaction. They can generate reactive oxygen species. And from our data, it appeared that the endothelial cell actually have a little bit more responsive to epithelial cells. So which cell source are responsible? What we find is that traffic and soil that contain iron, copper, titanium, and antimony are related to have better correlation with the ROS production. And to our surprise is that for this particular category, traffic and soil, the larger particle, the larger symbol here, is responsible for much greater effect, correlate better with the ROS production. And regardless of the location we collected, regardless of either summer or winter, but larger particle contributed much greater for this particular component. For residual oil, on the contrary, it's a smaller particle that are dominating and responsible for much greater change in this ROS production, and appear to be winter residual oil is much greater, have a better association with changes in ROS production in this particular assays. So overall, all the size, city, location, season are very important in terms of producing the obvious component that can produce obvious effect in cells, and PM fraction that that produce greater change is actually the larger the coarse particle, the particle between 10 and 2.5, that are producing greater effect than the fine and ultrafine particles. And most likely, the metal in these PM are associated with the changes in ROS production. And more recently, the people are concerned with the California fire, that what is the health consequences of this huge concentration of PM, and these PM actually produce a very strange orange smoke haze in San Francisco. So people are worried, what is the health consequences of exposures? And not only locally in California, but it also can blow into east, throughout the U.S. and impact it on the Midwest, as long as along all the way to the Northeast region. So when we plot the looking at the epidemiology study, we see this at very high concentration. Actually, the health effect is dropping. It becomes less, and so people are wondering if the higher concentration, it did not have the similar toxicities. And indeed, in Bangladesh, when we look at the PM larger than 100 microgram per cubic meter, actually have a less mortality and ED visit, the emergency room visit, than the particle at lower concentration. And we look at further into what is the reason for this change. We find out that most of the lower concentration is when there's a monsoon, and in the higher concentration time is in the non-monsoon when there's no monsoons. So what is the component related to this very different PM concentrations? And in the India continent, they use the crop burning, a lot of biomass burning, before the monsoon arrived to prepare the field for their crop. So because of the prevailing wind, the Bangladesh actually have very, very high concentration resulting from this during non-monsoon season, a lot of very high PM episode. And you look at the composition, and during the pre-monsoon season, you have a lot more potassium-related particle. Those are related to biomass burning, the green area. During the monsoon, those fires got burned, be put out, and the sulfur component actually produce much greater, have greater concentration. So if you plot the biomass burning versus the fossil fuel, the red line actually is dose response, mortality versus the concentration, mortality risk versus the concentration of PM actually have greater slope than the biomass burning. So the biomass burning have much less metals in their mass, therefore produce a flattening curve and have a much less dose response curve than the fossil fuel burning. So the composition actually will drive the resulting health effect. And keep in mind that even though these the biomass burning have shallower dose response curve, they usually come at much higher concentration. So overall, they still have a lot of impact in terms of health effect. And this is a quick summary. And fossil fuel combustion during monsoon season are dominated by fossil fuel, and they have much greater health effect during the fossil fuel had much greater effect than the biomass burnings. So overall, composition of PM is very important. We have to look at these carefully in order to figure out what is the source category that contributing to this obvious effect, so we can effectively control the source to reduce the PM exposure. And thank you very much. I would be happy to answer any questions.
Yeah, thank you, Professor Chen, for your wonderful and informative talk related to the air pollution and the cardiopulmonary health effect in animal and in vitro study. Any question from the audience?
Professor Chen, this is Ping Lin. Hi, nice to see you again. I'm wondering, you mentioned that the coal combustion is a major source associated with the plaque formation. And I'm wondering, in your experience, what would be the major source and major contributor, the major component? What's the difference in the proportion of chemical components in coal combustion that cause greater plaque formation?
We did an experiment in Gansu, China. You're probably aware of that. In that particular site, there is a nickel refinery. They use the coal to produce power to refine the nickel. And in the coal, they have arsenic and selenium. They are one or two of the higher dominating species in the PM. And so when we add these component into another PM mixture that do not have the arsenic and selenium, we can see that it restore some of the response to the overall PM exposure. So we believe that arsenic and selenium in the coal combustion probably related to probably contributing more than the other elements in the coal combustion. And keep in mind that PM is many different mixtures. So it's very difficult to say one or two or three component of the critical, but because the amount present in the coal combustion, the arsenic and selenium present in the coal combustion, is probably one of the reasons for the long-term effect. For the short-term effect, some other element may contribute to that, and we did not look at that carefully at this time.
Okay, so any other question? So Dr. Chen, you look at the particle. Have you looked at the gas phase for this coal combustion, biomass, or wood fire?
Well, we did that long time ago. We used to have, I used to work at MIT, so MIT have a great engineer. They produce this coal combustor that we can actually burn any type of coal and do the animal exposure. What we find out is that the coal actually produce much greater effect. We use the same system to burn wood too, and that produce much greater effect than the wood smoke that in laboratory setting. But those experiments are very high concentration and short term. So we haven't looked at that more recently to look at more realistic and in the conditions. The Bangladesh study, Bangladesh actually would be very, or India subcontinent would be very interesting to collect part of the season and look at, and also we probably will start a collaboration in the coming year with one of the Indian institutes and research institutes. The goal is to set up an animal exposure facility in India to do this type of study, different season, and looking at the contribution from during the monsoon and during the non-monsoon season, and see if we can distinguish that. So, so we haven't done that more recently, but we're looking forward to the future stuff.
Okay, thank you. So we already run out of time.
Thank you very much.
Dr. Chen, thank you again for your very informative talk. Okay. So right now we move to the second keynote speaker. Yeah, please, Dr. Lin.
Okay. It's my pleasure to introduce the next speaker. It's Dr. Huang Bingfang, Professor Huang Bingfang. Professor Huang, currently he's the Dean of College of Public Health in China Medical University. And Professor Huang got his PhD degree in Johns Hopkins University in the Department of Epidemiology, School of Public Health. And Professor Huang, he's an epidemiologist and has been trained in the environmental and occupational medicine and the environmental health. And currently his research interests focus on the health effect of the environment. And Professor Huang, he led a research group in the China Medical University and has published a lot SCI paper in great journals. And also Professor Huang also served as an academic and many academic editors and editorial board in many international journals. And Professor Huang, his research interest is major in two fields. First, in ambient air pollution and the birth outcome, including the children asthma, autism, and brain disease. And the second is focused on the indoor environment and the children's health. And today he'd like to share his work with us about the combined exposure to heavy metals in PM2.5 and pediatric asthma. So let's welcome Professor Huang for his presentation.
Good morning, ladies and gentlemen. It's my pleasure to share our work combine exposure to heavy metal in PM2.5 and pediatric asthma. My name is Bingfang Huang from China Medical University. This is our report outline. Introduction. Background. Long-term exposure to heavy metal may cause adverse health effects, including kidney, heart, liver, nerve, immune system, cardiovascular disease, respiratory disease, as well as neuropsychiatric disease. Exposure to environmental lead or broadly may associate with increased level of IgE. It would be cause immune toxicity and then cause inflammatory disorder, as well as allergic disease and asthma. So, according to the CDC in USA, they indicate global prevalence rate of asthma is up to 4.3%. More than 300 million people worldwide suffer from asthma. It is a big global burden of asthma. Then environmental factors will cause increase the level of immune IgE and cause inflammatory response, then cause bronchial response increase and chronic inflammation of airway, as well as bronchial obstructions, then cause respiratory disease such as asthma. So, to our best knowledge, probably the environmental factors and the genetic factor will play a very important role in the relationship related to the allergic disease. For environmental factors such as air pollutants, according to the dense study, they found SO2 and NO2 may associate with the asthma. Then, according to our previous study, we look at the prenatal and the postnatal exposure to PM2.5 and found that it may associate with pediatric asthma. And so far, we also know that sex may play a very important role. Boys tend to have a higher risk of asthma than girls, as well as maternal atopy and smoking during pregnancy as well. So, a longitudinal study in Australia that report long-term exposure to occupational heavy metal may significantly decrease lung functions. Then, it probably the blood lead concentration increase will disturb the homeostasis of trace element in systematic circulation and induce oxidative stress. Then so far, the current study mainly focus on occupational setting, exposure to higher level of heavy metals. Then little studies have been looked at the effect of children exposure to heavy metal in PM2.5 during pregnancy and infancy. So our study objective was that to explore the effect exposure to heavy metal in PM2.5 on asthma during pregnancy and the infancy period, and to identify the sensitive time windows and to clarify the ambient heavy metal on lung development. As well as we also try to look at the dose-response relationship, material and method. This is our study design. We pick up 4 main heavy metals in PM2.5, such as arsenic, cadmium, lead, and mercury. Now we try to use in weather research forecasting model combine chemical modeling to estimate daily heavy metal in PM2.5 concentration and corresponding to the maternal address to get each infant's exposure during pregnancy and infancy period. So our study population is located in the Taichung City from 2004 to 2011 and follow up until 2014. Here is our study area in Taichung. The main source for emissions is major steel plant and the coal-fired power plant, and as well as industry and the science park. At the beginning, we include 191 and 330 infants in Taichung City from 2004 to 2011. We exclude multiple births, stillbirths, birth defect, as well as preterm births. Finally, the study population was comprised of 171,281 children in our birth cohort. Then we also have some children that lost to follow-up, but the follow-up rate up to 99.75%. So we also identify about 18.26% the infant with asthma. For health outcome, the definition was that they receive at least 2 consecutive diagnoses from our physicians, either in outpatient or in patient-based records. Here, just show you how to assess our confounding factors. Our confounding factors selection criteria include that they should associate with the exposures and associate with our outcome of interest, such as asthma. So we elaborate socioeconomic status, maternal age, maternal atopy, maternal anemia, and maternal kidney disease may be a potentially confounding factors. So we controlling those factors in a multi-level regressions. Also, you may look at the green circles. They show it probably associated with the exposure, but not associated with the health outcome. For the red circle, they are not related either with exposure or asthma. For blue circles, they associate with asthma, but not really related to the exposure. So we so-called probably it would be the intermediate variable. For exposure assessment, we got top 75 lists of emission source from EPA, and we can estimate new emissions. Then we also combine meteorological initial and boundary condition models to estimate daily concentration of heavy metal in PM2.5 corresponding to the infants using their maternal residential address to estimate the exposure during pregnancy and infancy. So this work has been done by our colleague, Dr. Chuan Yao Lin in Academia Sinica. So here is Taichung City. Then we try to using this approach surrounding Taiwan. The main source for emissions probably is combustion coals that comprise of a couple of the heavy metal in the combustions. So this is the data we got from global forecast system as well as EPA. So here is the Taichung city map. We have a very large coal-fired plant in Taichung, and also some industry and science park located in Taichung City. For statistical analysis, we're using the Cox proportional Hadron model with time-dependent covariance to estimate the exposure may change over times. Then we also try to using distributed net nonlinear models with so-called Dllm models to look at the sensitive exposure time windows as well as the dose response relationship. So here is our result. So we found the age of onset of asthma is 3.41. Then boys tend to have a higher risk than females. Lower socioeconomic status, maternal age less than 30 years old, and the maternal atopy and maternal anemia is associated with increased risk of asthma. Then, in contrast, we did not find maternal smoking were associated with the asthma. Probably there is small number of the women that smoke during pregnancy. So we're using the IQR as an estimation of hazard ratios. So you can look at the distribution for prenatal and postnatal as well as overall exposure concentrations. This figure just shows you the concentration spatial variation in Taichung. This one, arsenic, cadmium, lead, and mercury, the spatial variation in the Taichung city. We also try to eliminate collinearity between the heavy metal exposures. So we try to use correlation coefficient to estimate these effects. We found arsenic and cadmium is highly correlated, and the lead and the cadmium also have a higher correlated. So we cannot put those four elements into the model at the same time. So that's the reason we have to be very careful to look at the correlations to avoid the collinearity in the models. So this figure just shows you we mutually adjusted for prenatal and the postnatal exposure period, and from the lead exposure during pregnancy is significantly associated with increased the risk of pediatric asthma during pregnancy. So this figure we so-called Dllm models, and then we try to look at the most sensitive time windows we found the exposure during the weeks between 1 to 14 and 21 to 40. The risk is significantly associated with asthma. Then we also try to look at the dose-response relationship. We found when the infant exposure over 26 times 10 power of -2 nanogram per cubic meter show a significant association, but later a little bit plateaus. So we also try to consider the heavy metal is a kind of the mixture. So we try to using the multi-component models, then we so-called co-exposure. As I pretty mentioned before, 4 elements cannot put it together at the same time in the model. So we using such as lead plus either arsenic or cadmium or mercury. They show a very consistent, positively and significantly associated with pediatric asthma. But we did not find they may associate with prenatal, postnatal exposure to any heavy metal exposures. So this figure just show you it is a very solid finding. Find here co-exposure to either arsenic or cadmium or mercury. The lead exposure show co-exposure to either 3 heavy metal during pregnancy may associate with pediatric asthma. So, discussions. We know the exposure pathway for heavy metal may be through air or diet. Drinking water, dust, as well as soil is the source of the heavy metals. Through probably inhale, ingestion or thermal contaminant that then go into the blood or urine or hair, then cause some health effects. So far, our idea is we try to look at the air heavy metals in PM2.5 through inhalation, then cause the health effects. So we still cannot rule out the other some possible pathway they will exposure to heavy metals. So that's our study's limitation. But when you're using these models, we can explore this effect in very huge population. So that's the main idea. When we compare previous studies, we found our study is quite consistent with the occupational exposure in high dose. So that is our result is consistent with previous high dose in occupational settings. So the exactly biological mechanism for why the sensitive time windows is between 1 to 14 weeks of gestation and 21 to 40 weeks of gestation. So far, it's not very clear. But when we look at the non-development, it probably locates during the stage embryo to pseudo granule and cuticular until the epilogue lesions. So we try to using the epi data to find this association, but so far we still need other animal models to support our result work as well as human models. So we hypothesis is that exposure to lead in PM2.5 through inhalation probably will increase the blood level of lead and increase the IgE levels, then cause type 1, we so-called the type 1 hypersensitivity, then cause bronchial response increase. Then it also will imbalance free radical versus antioxidants, then cause oxidative stress increase substantially. Then may cause chronic inflammation of airway, then finally cause asthma. That's our hypothesis. So our study also have some strengths because we did not using the selection approach. We cover all births born in Taichung during the study periods, the study population up to 300,000 births. So we so-called the nationwide population base to assess the effect of heavy metal in PM2.5 and the asthma. We also have very good high temperature resolutions because we have a daily exposure of heavy metal in PM2.5 estimations. And it is possible to look at the sensitive time windows. And we also have very detailed maternal and infant informations. So we can control those important confounding factors in the models. And also our spatial resolution is 2.5 kilometers. I think so far this resolution is good enough for epi studies. So we also have some limitations because for exposure assessment, such as major lead, arsenic, mercury, or cadmium in PM2.5 is very expensive and time consuming. So we are not be able to get daily observations for long times. We only can get the short time, probably is 2 weeks or 3 weeks measurement during in different seasons. So this model have some limitation to do the validations. Then we also have some possible selection bias because we follow up the children at least 3 years and up to 11, but some children may not is long enough to develop the asthma. Then we also know that maternal may change their residential address during the study period, but so far we only have the data at the birth who born in which residential address. So the other issue is genetic factors may also play a very important role, but we cannot control those important factors into account. But we have a prenatal atopy to do a surrogate representative the genetic information through the mothers. So this is our study's limitations. So our conclusion is that the study probably provides a new evidence the effect of heavy metal exposure in PM 2.5 on the development of pediatric asthma, and lead co-exposure to arsenic, cadmium, or mercury during the early and late gestational weeks show a significantly association with increased instance of pediatric asthma. But we know this is the very early pilot studies. We still need the other study to verify our findings. So that's our today's presentation. Before I end my presentation, I would like to thank my two students, Jia Yun and Cao Renzhong, as well as my colleague, Chuan Yaolin from Academia Sinica. We work together and get this work done. Thank you very much for your attention.
Dr. Huang, thanks for your presentation and very informative. And we have a question from the audience. Okay, I think Dr. Liu. His question is, you mentioned that the heavy metals are from different sources. And can you tell us how did you identify the personal exposure to heavy metal from PM 2.5?
Okay. This idea is I so-called the source is only picked up from major source from 75 days from EPA. So the main source is from our power plant or industry plant. So it's most of the pollutant is from our coal fire. Is called combustion. So that's the reason we try to look at only 4 heavy metals, because they cover about 90% combustion from coal. So that's the main idea. Then the other issue is we try to use in some initiators from weather parameters. Then this approach is developed from Academia Sinica from Lin Chuanyao 教授. So we try to using their air pollution map. The resolution is up 2.5 kilometers square. Then also the temporary resolution is daily. So that's the reason we can look at each children, combine their mother's residential address from birth, from conception through birth after 1 year. So that's a main idea. We try to use in their estimation and combine our address and to look at very detailed, sensitive time windows. That's the main idea.
Thanks. And any more questions from the audience?
Yeah, I think the audience have asked Dr. Huang, thank you for your wonderful talk. And congratulate that you already published this paper, this study in the high-ranked journal. And I look at the one main table, and you find the lead is the main culprit to cause asthma. But if you look at the postnatal exposure, actually there are some negative association and reach to the significant. Can you explain that?
Because we try to controlling prenatal and postnatal simultaneously. So that's the one way. It's probably highly correlated. So we try to look at the correlation between prenatal and postnatal. They show up to set, and the correlation coefficient is up to 70. So I think probably is one reason. When you using the when we try to estimate the header ratios independently during pregnancy or infancy, the association a little bit consistent for positive. But when we try to mutually controlling for that, one show positive, then the others probably show the negative. So after that, we try to consider the exposure for weekly maybe correlated each other. So we finally decide not just for time-dependent mutually controlling for the prenatal and the postnatal period. We also using with so-called nonlinear models try to see the effects. So after that, when you see the map for probably in the Dllm models, they show the positive association is during pregnancy, not for infancy period. But the association is a little bit varied, but not show very clear positive result. So probably the main result is the lag response relationship. So that's we try to use in two different models to show our data. So when you look at the model one, probably you will see one is positive for during pregnancy, then the others show protective association in infancy. But when you look at the whole period, the finding is mainly in the pregnancy period during this 1 to 14 and 21 to 41 weeks. So that's the main idea.
Okay, we have a lot of questions from the audience. And the first is Dr. Chen Longji asked, what is the source of the core used in the PowerPoint? And is there any plan to use the core with less metals? 大头黄，你可以看聊天区那个地方有留言。OK， 陈荣基老师问说，那个 core PowerPoint PowerPoint 用的 core 的来源 ，What is the source of core using plan？ 然后可能用比较少的金属的 core 吗？好，那其实 another audience asks what form of arsenic did you measure? What arsenic is oxide or trivarium, whatever.
Okay, the core probably we can use in non-lead core, but actually in Taiwan, if you would like save some cost, the cost quality is still some problem. But so far, we try to ask our government or our corporate to using the more clear core to generate our electricity. But actually, our goal is try to using the 天然气 for gas rather than using coal to get the electricity, and also try to looking for some clear energies. Then the other issues is the arsenic. We cannot distinguish 3 or 2. It's just a mixture. So in this study, we put it together, cannot distinguish which form. So that's our the other main limitations for the simulation approach.
Okay, and Julie has a question about, she asked, did you look at the, let me see, sorry. Atopic dermatitis in children? Yeah.
I think it's the other projects. Actually, it's possible to look at the atopic dermatitis, but I found the other research team, they also did this work and published already. So that's the reason I did not show this result in this talk.
Okay, and one more question, I hope. Okay, and food, the audience, one of the audience asked, the food may be the major, significant exposure source of these metals, and how to distinguish the exposure, the food exposure contribute to the personal diet, from the personal diet. The food.
So in our study, I think we are not able to consider the food consumption may contain some lead. So this is our limitation. So in the other way, probably we also can using some food items and try to look at if any possible for lead contaminants through injection. So in our study, I think we have not able to answer this question.
Okay.
So Dr. Fang, in your study, did you have the personal information? Because I find out that you have the cigarette smoking information. So I'm just wondering, how about secondhand smoke?
Actually, this is maternal smoking during pregnancy. So we did not do the personal data collection. It's through our birth registration. So that's the reason some personal information cannot get it in these studies.
I have the last question from the audience. In the multiple exposure model, and you found a significant positive association between air pollution exposure during the prenatal period and asthma, but significant negative association, okay, during the postnatal period. So do you have any comment about the negative association during the postnatal period?
I said it's not really negative association because we are controlling for the same exposure for postnatal and prenatal at the same times. This caused the collinearity, where cause this result is a little bit strange. So finally, we're using the second model, I so-called the Dllm Models, and I try to look at the whole periods from prenatal and postnatal, and through the whole process in weekly. So the weekly results show the positive results only in pregnancy. For the postnatal period, they show a little bit association, but not really negative and protective. So my point of view, probably the second model is more appropriate to analyze those kind of data.
Yeah, there one more question come from the audience 2 minutes ago. And the question is, okay, in country without lead exposure, will the prevalence of pediatric asthma still increase? And he asked, how can you explain this?
But actually, for our previous study, the main source is probably PM2.5 is the one risk factor for pediatric asthma, will cause the pediatric asthma increase substantially. But actually, we try to look at the components. That's our idea. So probably for asthma, I think the environment will play some roles, as well as the climate change, something like that, or even the heating or too cold. So in our point of view, probably the environmental factors should pay more attention on that, because the genetic factor did not change over time, and they will not cause the asthma increase substantially.
Okay, I think, okay, because of time limit, we have delay for 5 minutes. No. So let's thank Professor Huang again for his excellent talk. And so we will have a break after this section.
Thank you.
Okay.
Thanks. Okay. Thanks again for Professor Chen Longji and Professor Huang Bingfang. So wonderful informative sharing and discussion. And thank you, Professor Wu and Professor Lin, great introduction. Okay. So 谢谢陈龙基教授还有黄平方院长为我们带来这么精彩的报告，这样，然后也再次感谢我们的一个主持人吴医师还有林研究员的一个介绍跟讨论。Okay, so due to a slight delay in this meeting, so let's rest for maybe 15 minutes. The next speech will start at 11:20. Thank you. 因为这次会议时间有稍微 delay， 所以我们先休息个15分钟，然后下一场将在11:20开始进行下一场的演讲。谢谢大家。Okay, ladies and gentlemen, and now for a third keynote speech. Speaker is Dr. Chen Lingzhi. We are honored to have Professor Zhuang Hongyi of Kaohsiung Medical University and Dr. Chen Yuzhen of National Health Research Institute serve as our moderator. Now, let's welcome Professor Zhuang and Dr. Chen. 此次大会我们第3个讲者是中研院陈林志研究员，然后我们大会很荣幸邀请到高雄医学大学公共卫生学系庄弘毅庄医师和国家卫生研究院环境医学研究所陈玉正副研究员担任主持人。现在让我们先欢迎主持人庄医师和陈副研究员。
大家好 ，Hello everyone online. Okay, I'm Hongyi Zhuang from Kaohsiung Medical University. Now I have the honor to present online, and it's my honor to introduce Professor Longji Chen, 陈林志研究员。Longji Chen, the topic is Internet of Things for Air Quality Monitoring, past, present, and future. Professor Chen has much experience on air pollution data. So currently he serves in our academia Sinica, in the Institute of Information, and he served as a director in the institute for coordinated data, scientific data of air pollution. And now he has a big project, so-called Airbox project. It's including 59 countries. So we are very happy and very honored to invite Professor Chen Lingzhi 研究员 to come to our conference and to present the air pollution data monitoring, air quality data monitoring, especially at the present and in the future. So let's welcome Professor Chen Lingzhi 研究员. Thank you.
Hello everyone, this is Longji Chen from Academia Sinica, Taiwan. Today, the topic of my talk is the application of the Internet of Things in air quality monitoring. I will use our project called Airbox as an example and discuss how the Internet of Things can be used for air quality monitoring, as well as how we make sense of Airbox data to address problems that most people are concerned about. Before we start, I think we should give a brief introduction to the Internet of Things. The Internet of Things is composed of multiple sensing devices, which are connected to the Internet through various methods, such as Wi-Fi, Bluetooth, 3G, 4G, and 5G. Each device measures its use and contributes to the backend database at a predetermined rate. The backend server receives the data stream from all the sensors deployed in the field, which will soon become a large-scale time series or spatial temporal data stream, which can be visualized, processed, and analyzed to provide insight into the overall scenario. In addition, using the collected big data, we can also apply all kinds of AI and machine learning techniques to even deepen our investigation and figure out the knowledge, wisdom from the data. Today, you may have heard many so-called smart blah 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 applications, such as smart city, smart healthcare, smart home, and so on and so forth. And these smart blah 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 are all built based on the Internet of Things to collect data, process information, and generate knowledge, wisdom from the data. This is why we call it smart. In this presentation, I will use our Airbox project to show how the Internet of Things can help air quality monitoring and how much we have achieved using the data collected from the Airbox deployments in the past few years. Let me show you some quick facts before and after our deployment in the next slide. As you can see, before we started the Airbox project, if Taiwanese were interested in air quality data, they could only rely on 77 professional EPA stations, which will give you the measurement results every hour. However, today, if you want to know the air quality in the area around you, we have deployed more than 12,000 devices, and each device returns a measurement result every 5 minutes. It is conceivable that under very intensive deployment and frequent sampling, we have greatly reduced the spatial and temporal granularity of air quality monitoring, so we can answer people's inquiries about air quality in their microenvironments. Of course, since our system uses low-cost air quality sensors, it may lose some accuracy if compared to professional EPA stations. However, it has also proven to be a good research problem for big data analysis and artificial intelligence, and I will show you how we have overcome these problems in the following slides. Now, let me take a few minutes to take a quick look at the development process of the project. Our project has 3 components. The first one is to enable this technology and make low-cost air quality sensing possible. We started this project from scratch 7 years ago and gradually learned how to assemble sensors, how to make PCB boards, how to use Wi-Fi, Bluetooth, 4G to send sensor data to the outside world, and how to use 3D printing to design the housing. We also evaluate various low-cost air sensors for professional equipment and find good quality sensors that can be used in our projects. Fortunately, we found a low-cost PM2.5 sensor with good performance. The second component of the project is to empower people to use this technology and copy our work to make their own work. We decided to use open hardware which is commercially off the shelf and easy to be used and even modified when needed. We also published our source codes on GitHub, so people can track and even contribute our codes. Finally, we decided to publish all the collected data in an open data format and in real time. There are several reasons for this. Number one, we hope to reduce technical boundaries so everyone can easily join us. Number two, we want to build trust between the participants and our team because everything is open and public. Number three, we hope to recruit more diverse people. For example, people can join our project by making devices to contribute data, fixing our codes, or contributing new features, or just using our data for their research or developing new applications. In addition, we have designed multiple visualization tools to help people understand the data collected from the Airbox project. We found it very useful, especially for using our system to promote citizen science. The third component is to engage people to participate, collaborate, and contribute. The project was originally an academic research project, and then we worked with a local community called Location-Aware Sensing System to recruit people from different backgrounds. Then, we were fortunate to receive a 4-year government grant to deploy Airbox devices in every K-12 school in Taiwan. The focus of the project has also changed over time. At the beginning, we focused on sensor deployment, and then turned to data analysis after collecting a large amount of data from the deployment. Now, we focus on interdisciplinary cooperation to solve real-world problems. Therefore, the project has established a very active and healthy ecosystem involving academia, communities, industries, governments, educational schools, and teachers. These 5 components voluntarily contribute to the system and help each other to keep the ecosystem circulating. To date, the project has deployed more than 12,000 devices in 59 countries. We have established close collaboration with major research universities in Taiwan and have close collaboration with other major low-cost air sensing projects around the world, such as the Array of Things project in Chicago, the AQNU project in Utah, the Smart AQNet project in Germany, the City Air project in Russia, the Dustboy project in Thailand, and Purple Air in the United States. In addition to deploying and setting up the network, we also put forward some research results. For example, we propose a comprehensive evaluation that compares our equipment with professional equipment and evaluates the consistency performance between Airbus devices. Of course, the results are very encouraging and promising. In order to handle thousands of real-time IoT data streams, we have also developed a powerful back-end architecture that can monitor a large number of devices, correctly store the data in different databases, and publish the measurement results in JSON or CSV format in real time. Using the collected data, we implemented an inverse distance weighting algorithm to interpolate the air quality between Airbox devices. We took a snapshot of the visualization results every 20 minutes and made animations to visualize how the air quality distribution changes over time. For example, on the right-hand side, the animation shows the long-distance transmission of dust and pollutants from north side of Taiwan to the south side. The animation was produced in January 2017. This is the first time in history that we can crowdsource low-cost air sensor data and visualize such pollution events with such granularity. In addition, the second animation was shot during a cultural event in central Taiwan. During the event, people burnt incense and gold money almost at the same time to celebrate the birthday of the most important god. As we can see in the animation, the air quality in central Taiwan turned purple, indicating the PM2.5 concentration was very high, and turned back to orange color after the events. It turns out that it's the perfect material for environmental education because human behavior may affect our environments, especially when a large group of people do things together. We also considered the data quality issues in our system and implemented an anomaly detection framework called ADF to use spatial temporal data analysis to detect pollution events and abnormal devices. This work is actually very challenging because several reasons. One, the accuracy of the device is not as good as that of the EPS station, so our solution must tolerate slight errors in the data stream. Number two, the device is not time synchronized, so our solution must implement the concept of time window slice in our data analysis. Number three, the solution must distinguish between outliers and air quality events, even if they have similar patterns in the time series data stream. And number four, the solution must be simple and fast in order to be able to support online calculations and publish results in almost real time for further applications. The idea of our method is to detect two types of anomalies from the sensor data streams. The first type is called spatial anomaly, which means that the airbox device behaves differently from other nearby devices. The second type is called time anomaly. That means the measurement data of airbox changes drastically in a very short limit time. Based on the frequency of these two types of anomalies, we can calculate the critical values of each airbox device. And based on the appearance patterns of these two types of anomalies, we can infer the cause of this anomaly, such as the device is located indoors, there is the fixed source of emissions near the device, or a burning event is occurring during near the equipment. As you can see in the figure, we have successfully implemented our anomaly detection framework and released our analysis results to the public almost in real time. And the results of our analysis were imported by Taiwan's hacker community, Zero Government, and they create a very beautiful data visualization on their website. In their design, they provide different icons to represent airbox devices with different attributes so that people can easily understand that the devices when viewing the PM2.5 map website. We also applied machine learning to the airbox dataset and contribute on PM2.5 data prediction research to predict short-term PM2.5 concentrations. Here, I mean prediction the PM2.5 concentration in the next 1 to 5 hours. Compared with the traditional data prediction problem, short-term PM2.5 prediction is very challenging because you must train the model, update the model frequently, and give the prediction results in a very timely manner. For example, you may only have 1 minute to complete the entire work and generate prediction results for 10,000 airbox devices. To solve this problem, we consider the solutions in 2 dimensions. One is accuracy, which means we want to have a solution that can provide us with as accurate results as possible. To this end, we have applied modern machine learning techniques such as neural networks or even deep learning to achieve high precision predictions. But the training phase may take too much time to make this solution feasible for our purposes. And the other dimension is scalability, which means we want to generate predictions in a limited time frame for as many airbox devices as possible. For example, we can model the prediction problem as a matrix optimization problem to find a transition matrix between two consecutive time slots. Then we can apply the transition matrix to generate data prediction results for the next time slot very quickly, even though the error is also becoming larger and accumulated. Obviously, these two dimensions are contradictory, and there must be something in the middle between the two extremes. So, we studied different clustering techniques to identify different airbox groups with similar spatial temporal behavior and trained models for each group. And then, we applied this model to other airbox devices in the same group to generate prediction results. As you can see on the figures, the calculation time has been significantly reduced using our method, while the accuracy performance is still acceptable. This is just an attempt to strike a good balance between accuracy and scalability, and more research on this topic is still in progress, and we hope that there will be new results very soon. Next, once we obtained the real-time PM2.5 data from intensive deployment and short-term forecast data from forecasting services, we developed a new navigation service called Clean Air Routing to provide people with minimal PM2.5 exposures routes in the city. By talking about minimal PM2.5 exposure, we are talking about the total amount of PM2.5 accumulated over time during your movement. As you can see, if you want to move from the red dot on the right to another red dot on the left, Google's shortest path algorithm will provide you with a great path. However, our clean air routing algorithm will provide you with a blue route that will turn to the riverside and then to the downtown city, where there are very few vehicles at that time. The total PM2.5 exposure score dropped from 75 to 59, but the travel time was about 30 minutes longer than the shortest one. The clean air routing application is just an attempt to design an innovative application based on a low-cost air sensor IoT system. By providing more fine-grained spatial temporal measurement data, we believe that more and more new applications will be created, and these applications will enable data-informed decision-making in the long run. These applications are very important to IoT systems, not only because they would not be possible without IoT deployment, but also because they can understand IoT systems and make the IoT visible to the public. Recently, we also work with cross-disciplinary experts to address classic problems in other fields. For instance, in spatial statistics and public health, it is essential to predict ground-level PM2.5 concentrations using nearby air quality station data, and the results can benefit health impact assessment of cohorts with PM2.5 exposures. Traditionally, the prediction considers EPA station data, meteorological data, and spatial attributes. On top of the state-of-the-art, we consider data from the airbox network and adjust the interpolation parameters based on airbox data analysis. The results are very promising, as the R-squared value is more stable at 0.87, and the RMC is reduced to 4.1 microgram per cubic meters. The result of this study may benefit many ongoing public health studies in finding the correlation between PM2.5 exposures and different diseases, and we are still working on improving prediction accuracy of the work and looking for collaboration too. Currently, we have also established a dynamic calibration framework in cooperation with Taiwan's EPA to calibrate low-cost airbox data. First, we selected 31 EPA sites as reference points, and each site deployed 2 airbox devices to conduct a parallel comparison testbed. Then, for each reference site, we considered more than 200 model configurations and selected the one with the best accuracy performance as the reference site's calibration model for that day. Then, for each airbox device in Taiwan, we find the reference site closest to the device and apply its calibration model to the airbox. We understand that there may be some models that can provide even better accuracy performance in calibration, but given our limited knowledge and computing resources, this is the best effort we can achieve so far. Based on the calibration data, we also give activity suggestions when we release the measurement results to the public. In addition, we also publish the model on the website in binary form, as well as detailed parameter configuration so that people can reproduce the results. We believe that keeping everything open during the calibration process is very important because this is the best way to build and maintain public trust. This is also important for the research community because we need to ensure that the results can be reproduced in the future. So far, I have shown you some research results of airbox. Next, I want to share with you some interesting findings that we learned from experiments when promoting citizen science and environmental education. For example, we can use the mask of different materials to package our device and understand which mask material can best prevent PM2.5 exposures. We can also use our device to measure the PM2.5 concentration before and after turning on the air purifier to compare the performance of different models of air purifiers by crowdsourcing tests to the community. We also installed airbox in my vehicles and conduct a very simple experiments to study the air quality of the interior recirculation and exterior air. This airbox is the spatial version made by my team. It has PM2.5 and CO2 sensors. When I got in the car, the PM2.5 and CO2 readings were about the same as the outdoor conditions. And I started using the internal air recirculation drive. As you can see on the slide, the PM2.5 curve slowly drops because the air inlet is equipped with the filter, and the air is getting cleaner after being recirculated. However, you will find that the CO2 curve grows very fast, reaching 2000 ppm after 20 minutes. We know that after a period of such high concentrations, people may feel sleepy and inattentive, which can be dangerous when driving at high speed. Then I switched the air conditioner to outside air mode, and the CO2 concentration quickly dropped to less than 700 ppm in just 3 minutes, which was acceptable. The PM2.5 level also increased to 32 microgram per cubic meters, which is approximately equal to the outdoor PM2.5 level. It turns out very interesting that when driving on the road, we need to switch back and forth between air recirculation and fresh air mode, so that we can achieve a good balance between energy saving and good air quality in the car. So, what's the next step for the Airbox project? There are still many open challenges ahead. For example, in terms of equipment hardware, we hope to integrate additional sensors into the system, such as CO2, TVOC, sound, and light sensors. We hope to study energy harvesting on Airbox and make the system self-sustaining in the future. We hope to strengthen the security design of our system and gradually offload some data analysis and machine learning tasks to edge IoT devices for edge computing. In addition, in terms of big data, we hope to deepen our research on multi-resource data fusion and use cyber-physical social data as a whole to understand the interaction between the environment, the cyber world, and the social media. We hope to cooperate with environmental experts and apply artificial intelligence technology to strengthen model-based simulation research. We hope to combine AI technology and GIS applications to form GeoAI and embed this intelligence into future database systems. Finally, in terms of applications, we hope to shift the focus to indoor scenarios and promote more interdisciplinary research, collaborations, and international cooperation. We hope that all these efforts will help to promote data-informed decision-making in the near future. Okay, let me end this conversation. In this talk, I introduced an application of the Internet of Things in air quality monitoring. The project is called Airbox, and there are several lessons that we learned from the project. Number one, open is the key to making things possible and making the overall solution scalable. Number two, the power of the Internet of Things is to make sense of data. Number three, there are many challenges and research issues in the future. I encourage you to think about the must-have problems rather than nice-to-have problems, because this is the only way to make your system meaningful in the real world. There are still many unsolved challenges, and I look forward to working with you in the near future. This is the end of my talk. Thank you very much for your attention.
Thank you. 玉正，交给你。
Okay. Thanks for Dr. Chen's presentation. Now we for the open question. Any audience in online or internet? Before someone asking, I have one question. I think the Dr. Chen's IoT project or large project is really successful. Not only researchers or government join this project, but also our community residents. And I heard many people from the Facebook to talk about the large projects. And then my first question is based on your past experience for this project. And could you please share us more stories and about what benefits when our community residents are using Airbox sensors or local sensors, and what can they get, and then to improve their air quality? Do you have any story from that?
Okay, thank you, Professor Chen. So actually, there are many stories. So and I think for the low-cost air sensor, it can provide you microenvironment information. So we found many people they use a micro sensor, the local sensor, to know what's the current PM2.5 concentrations in his surrounding area. So if you have kids have asthma or some kind of respiratory disease, then you are very sensitive. I mean, they are very sensitive to the air quality, and you're also very concerned about the air quality. So they use the tool to help them to prevent the exposure to such high concentration and also to take some proper response. For example, you can turn on the air purifier or close the window, so on and so forth. So there are many such stories, and yeah.
Okay, and someone asked what price about this device?
Well, it's around 3,000 to 4,000
NT dollars.
TD. Yeah, or say 100 USD. Yeah.
Okay. And someone's asking how to involve people implement collaboration to censor air population.
You mean the calibration?
No. Yeah. How to involve people implement collaboration. Yeah, to censor air population.
Okay, so I work with many researchers, and there is everyone has different purpose for this collaboration, but the common interest is open data. So I am happy to provide such tool, such data platform, and I also provide data access. So if you are interested in this project, you can use the machine. They will send data to my server, which is reliable, and I give you the open access to the data. And also we can have more such talk, and I know many experts because many people talk to me. So I know a group of good people like Professor Chen. You are also one of the collaborators. So I think this is a very positive, healthy ecosystem. So everyone interested in local sensor, you have your request, and I can help you even customize the device to provide you some special functions. So yeah, just do it and talk to me if you have any special interest. Yeah.
And how many countries has use this device for air quality monitoring?
Okay, it's very difficult to give you the exact number, but I already observed people from 59 countries.
Oh,
they use my device. Yeah.
Okay.
I have a question to Lingzi. Since it's Internet of Things, how about the DPRO? I mean the database. Does the database open for scholar or research?
Well, we have we have different methods for you to upload your data. That's how data from your device to our server. And then we also have web access. We have provide some URL specially created for you. Actually, it's the open API. Well, you can just recruit some student who knows internet programming. They read our document, then they know how to get the data back to your device, your computer. Yeah.
Okay.
Thank you.
I have a really challenging question for you. As we know, the recent big news from the WHO is the announcement of updated air quality guideline beyond COVID-19. Okay. For instance, the annual and the 24-hour average concentration of PM2.5 has been subject to 5 and 55 microgram per cubic meter. Okay. And I guess no longer the Taiwan EPA will take this guideline to set lower limits of PM2.5. And as we know, the recent air quality in Taiwan overall becomes better compared past, and the PM2.5 concentration go to lower. My question is, the accuracy and the precision of PM2.5 low-cost sensor have been questioned, in particular in detection of the lower PM2.5 level. Could you please comment this new challenge of the low-cost sensor facing lower ambient PM2.5 in the data science?
Okay, it's a very good question actually. So I think it depends on your purpose of using this low-cost sensors. Since it's low cost, so we don't expect it to be super accurate, super precise. it's impossible, right? So we will lose some accuracy, that's for sure. And when we talk about the new WHO's the guidelines, the concentration, PM2.5 concentration is very low actually. And I will say if the air quality in Taiwan is already very good, it's under 10, not 5, under 10, then actually no one needs local sensor. The reason we need local sensor is because the air quality is not good. We want to protect our family. We want to protect our kids. So we want to have early warning system. That's why we need to have local sensor. But if we want to make sure whether we are under the WHO guideline, we still need to go back to professional devices.
Okay. Yeah.
Thank you.
Yeah.
Okay. Does anyone have a question for Linzi? Currently, there's 19 auditors online. So
I have one question for
okay. Please.
In your slide, for your next research, it's about the low-cost gas sensor. Okay, do you have any comment on that or progress research?
Actually, no. I know TVOC is mature enough, and many people are already using it now. And in addition to TVOC, maybe ozone will be the next one to come, but it's still not ready yet for if you want to have very serious applications.
How about the NO2?
No.
No,
NO2
is it possible to develop that?
Well, it's very unstable.
Okay.
Depends if you want to have an NO2 sensor and you agree to recalibrate the sensor every week, then probably you can use it. Yeah.
Okay.
I see Leon online. Leon, have any question to Linzi?
Sorry, no, this is it's a wonderful presentation. Thank you very much for insightful knowledge. Thank you.
Thank you.
Thank you. So it's time.
Yeah.
12. So thank you, everyone. Thank you, online, everyone. We think it's lunch time. So let's end in this section. Thank you, Linzi, and thank you, Yuzheng and Leon.
Thank you. Thank you.
Thank you. Bye-bye.
Thank you, Dr. Zhang.
Thanks for Dr. Chen Linzi's amazing presentation, and thank you, Professor Zhuang and Dr. Chen, great introduction. 我们谢谢陈林志研究员为我们带来这么精彩的简报哈，然后也再次感谢庄医师还有陈副研究员的介绍哈，谢谢。Okay. The session in the afternoon will begin at 13:13. At 13:13, please come back on time and thank you for your cooperation. 早上的议程我们就到此先告一段落哈，那下午的议程会从下午1点30分开始哈，下午1点30分，请大家准时回来哈，谢谢大家的合作哈，谢谢。